Okay, so with percent composition, we start by finding the molar mass of the whole thing. We divide each element by that molar mass. So we're looking at this last one here. And if we look at calcium, it has 40 plus how many nitrogen atoms do we have? Can you see that compound okay? CaNO3, 2. Okay, so 2 nitrogen atoms, which each nitrogen atom is 14. Okay, and how many oxygen atoms are we working with? 5 or 6? 6. We multiply those. Okay, whenever our 2 is outside of a parentheses, we multiply here and we multiply here.
Why does nitrogen get 2?
Because this NO3 is a compound in itself, and it says we need 2 of these whole compounds. That's what the parentheses are telling us. Okay, so that means we need 2 nitrogens and we need 6 oxygens. Okay. So my total molar mass, I got about 164. Would we agree with that? Okay. All of these elements are good to go to a whole number. Okay. So now if I want to find just the percent mass of only calcium, I don't need to worry about nitrogen or oxygen. I'm only looking at calcium. So how many grams of calcium are found in this total sample? 40, right? If the whole thing weighs 164 grams, we know that 40 of those grams come from calcium. Okay, so 40 divided by 164 gives us 24.4%. Okay, and if I had asked for the total percent composition, we would have done nitrogen, right, divided by 164, and we would have done oxygen divided by 164, and we would have gotten a percent of nitrogen and a percent of oxygen, and hopefully all of those percents would have added up to 100. Okay, does that part make sense? We would have had 3 different percentages if it would have asked for total percent composition. Okay, so I'm going to give you another example. You're going to do one of each on your own. Okay? Okay, so let's find the percent of lithium in Li2SO4. And then I want you to find the percent composition, which means all of them, of MgCO3. Okay, so 2 different problems here. I want you to solve each of these on your own. On our percent of lithium, what do we take? Did we all agree that this was about our molar mass, around 109.8? Okay, 110 if you rounded that to 7. What are we going to take divided by that molar mass? Good. we take 13.8 because there's not just one lithium atom in that compound. There's two. So you need to take into account both of those lithium atoms. So if our whole compound weighs 109.8, we know that 13.8 of those grams are found from lithium. So we take 13.8 divided by 109.8, and what do we get for our percentage? Okay. Yeah. Between 12.5 to 13%. Yeah, I had 12.56%, so about 12.6. Okay, depending on where you rounded that up. Okay, are we in the ballpark there? Somewhere around 12.5%?
Well, you could count it off if you put 13.
No, probably not. When in doubt, I would like you to leave a decimal place though. Okay, if it's a 0.9 or something, I'm okay with rounding, or 0.1 or whatever. But if we're in the middle range like that, I'd probably like you to keep 1. Okay? All right, the same goes for the bottom one. We need percent composition, which means we're looking at all of them. So for magnesium, we're taking 24.3 divided by our total. Did we get 84.3 for our molar mass? Okay, so what was our percent of magnesium? 28.8. Okay, and this is Mg. What's our, okay, for carbon, we take 12 divided by 84.3, and we get what percent? 14.2. And that's carbon. And for our oxygen, we take 48 divided by 84.3, 57%. So if we add all those together, 28 plus 14.2 plus 57, 100. Perfect, right? And if we get 99.99101 something, we're okay.
So I did 29% and 14%.
Okay, yeah. It comes out to 100 still, but when we're in doubt, we're going to keep that decimal place. We're just more exact. Okay. All right, very good. Any questions with percent composition? All right, very good. So that you will need to know for your quiz next class. Okay. Okay, so now we're going to get into some more conversions. Right? We did basically meter to centimeter conversions, inch to centimeter conversions. We did all those conversions at the beginning in terms of the metric system, and now we're looking at conversions between the amounts of a given sample. So we're going to be able to take grams of a sample and convert it to moles of a sample, and moles of a sample and turn it into molecules in a sample. So we're looking at a quantity of a substance, and we're going to be able to express it lots of different ways: grams and moles and molecules.
Is this going to be on the quiz?
Nope.
Is this chapter 2 though?
Mm-hmm. Okay, first of all, before we start doing any math, I want to talk a little bit more about what a mole is. Have you heard the term mole before in a scientific context? Not the animal. Yes or no? Yeah. A mole is a unit of measurement. And the unit that it's, or the amount of substance that it's showing is very large. Okay? So let's think about this for just a second. So a mole is a very, very large unit of measurement. If I would ask you how many baseballs are in a dozen, what do you tell me? 12, right? And how many roses are in a dozen? And how many donuts are in a dozen? Right. So does it matter what substance we're talking about in terms of a dozen? No, a dozen is always 12. So a mole works the same way. It's just on a much bigger scale. Okay? So 1 mole, right? We know 1 mole is equal to not 12 of something, not 20 of something, but 6.022 times 10 to the 23rd of something. Okay, so it's a huge number. Right? If we had a mole of baseballs, it would take up the whole school. right? You've got millions and millions and millions of baseballs. Okay, so 1 mole of anything is 6.022 times 10 to the 23rd of that object. Most of the time, we think about it in terms of molecules, right? This many molecules is in 1 mole of those molecules. Okay, that's usually what we think about it in terms of, right? Or this many atoms is found in 1 mole. Okay, that's most of the time what we're talking about. Okay, and what do we also know about 1 mole in terms of mass, in terms of grams? Yeah, Evan.
1 mole equals 1 gram?
Not necessarily, no, only for hydrogen. Yeah, because when we look at grams per mole, right, grams per 1 mole, this is the molar mass. Right? So 1 mole of oxygen atoms would weigh how much? 16 grams, right? We find that right off the periodic table. So 1 mole of carbon atoms would weigh how much? 12 grams, right? So what we're also looking at here is that we could say 12 grams of carbon 12 grams of carbon atoms, right, would be this many carbon atoms, right? Because we know it's equal to 1 mole. Okay, are we kind of on the same page there? All of those 3 things tell us the same amount of carbon that we're looking at. 12 grams and 1 mole and 6.02 times 10 to the 23rd carbon atoms. That's all the same number, the same amount of substance. It's just 3 different units of measurement for that. Does that make sense, kind of, or not so much? A little bit? Okay, so now we're going to look at converting basically from grams to moles. Okay, if I give you the number of substance in grams, let's say I have 100 grams of carbon, how many moles of carbon is it? Right, that's what we're going to look at. We're going to start there, then we're going to work our way to molecules a little bit. But I want you to have an idea about what the mole is. It's a really, really, really large unit of measurement. So usually we deal with small numbers of moles. Okay, from grams to moles, we're going to start with a T-chart here. So I'm not going to blah, blah, blah. Okay, we're just going to go to example. Okay. This is like back to T-chart world, okay? So conversions always deal with T-charts, okay? Or I always like to deal with T-charts. So the first part of any T-chart is to write what we know. Write what we know. Okay, so 74.2 grams of lithium chloride. Okay, and it's important to keep that label there. For right now, it's not a huge deal. Much later in the year, it will become a bigger deal, so it's a good habit to get into. Okay. So I want to go from grams to moles, right? So I wanted to figure out how many moles there are. So I write what I know and I draw my T. Okay, is this coming back to us a little bit? Okay, if I want to get rid of grams and go to moles, what's the next placement on my T-chart look like? Good. Grams of lithium chloride goes on the bottom, and mole goes on the top. And mole is just abbreviated MOL. Okay, so if we know that 1 mole of LiCl is equal to, nope, sorry. I'm backwards, okay? If we know that 1 mole of just lithium weighs 6.9 grams, right? We can find how much 1 mole of lithium chloride weighs just calculating its molar mass. Okay, so in these T-chart, the mole always gets the 1. It always gets a 1. Because we're going to tell how many grams of this substance can be found in 1 mole of that substance. Okay, so that means that this number right here is going to be the molar mass. Okay, so we need to calculate the molar mass of lithium chloride. Okay, so what do we get for molar mass of lithium chloride? What number goes right here? 42.4. Lithium I have at 6.9. Chlorine I have at 35.5. So now we've canceled grams, and we're left with moles. Is that what we want to be in? Yes. So how do we finish the math on our T-chart? Do you remember? Multiply across the whole top, divide by the whole bottom. Multiply across the whole top, divide by the whole bottom. And that's what our final answer should look like. We should have units on there as well. So if we want to go from grams to moles, we divide by our molar mass. Okay, that's it. The T-charts are going to become more complex when we add more parts to it, but for right now, that's as difficult as they get. So I want you to now check to see, is your answer reasonable? Does it make sense? And this is how you can check that. Okay? We know that 1 mole of lithium chloride weighs 42.4 grams, correct? Okay, we know that. We just calculated it. 1 mole weighs 42 grams. Did we start with greater than or less than 42.4 grams? Greater than. So we should end up with more than 1 mole. Isn't that right? If we know that 1 mole weighs 42 grams and we started with 74 grams, that means we're dealing with more than 1 mole of our substance. Okay, does that make sense? So that's how we check to see, does our answer make sense? Did we accidentally flip-flop our T-chart? Because sometimes that happens, right? Okay, are we on the same page so far? Okay, another thing is that when we're dealing with grams, we can have all sorts of numbers. In the ones, in the hundreds, in the thousands. We can have lots of different numbers of grams. When we're dealing with moles, we usually have very small, reasonable numbers. Okay, usually between 0 and like 20. We don't deal with like thousands and thousands of moles. So if you get a number that's thousands and thousands of moles, that means you might have done something wrong. Okay, most of the time, for 90% of our problems, the number of moles that we deal with is a smaller number. Okay, because it's a large quantity of the substance, so we're looking at a small unit here. Okay? All right, any other questions? Okay. Let's go now from moles to grams. Okay, so this time we went from grams to moles. Now we're going to go moles to grams. How many grams, so I'm going to put my question mark there, are in 0.42 moles of this substance called magnesium nitrate? So we start by writing what we know. Okay, and in my T-chart, what should go on the bottom here? What am I trying to get rid of? Moles, and I'm trying to go to grams. Okay. Okay, and what does moles always get? 1. The 1. It always gets the 1. And what number goes right here with grams? The molar mass. Okay, this should always be molar mass that goes with grams. Okay, because we're telling how many grams is in 1 mole of that substance. And that, in and of itself, is the molar mass. Okay, so if I'm calculating molar mass of magnesium nitrate, I'm going 24.3 plus how many nitrogens? 2. Plus how many oxygens? 6. These two get multiplied together. Okay, the 3 and the 2 get multiplied together. Okay, so for my molar mass, I had about 148.3. Would we agree there? Okay. So now, I've canceled moles. I'm left in grams. Is that what I want? Yes, right? I'm left in grams. That's what I want. So I multiply across the whole top, divide by the whole bottom, which is a 1. So that doesn't lead me to do much on the bottom. 62.3 grams of MgNO3 2. Okay, how are we feeling? Okay so far? Okay, so let's check now, does our answer make sense? We started with, for all intents and purposes, right, around a half of a mole. Okay, a little less than half of a mole. And if we know 1 mole weighs about 150 grams, roughly, right, I'm just thinking rough numbers here. If we know that 1 mole weighs about 150 and we know we have a round half, a little under half, does our answer of 62 make sense? Yeah, half of 150 is 75, right? So a little under half could be in the 62 range, right? If we would have ended up with 400 grams, we would have known we did something wrong, right? Because half a mole would not give us 400 grams of this compound. Okay, does that part make sense? Okay. Any questions here? Let's try the next two on your own. Okay, so these last guys right here, we're going to try on your own. Uh-huh. For calcium carbonate, what'd you have, Katie?
1.48.
For molar mass, 100.48. What did you say? Just for molar mass for this one, sorry.
Oh, 216.7.
That's not quite what I had. I had 100.8 also. Or around 100. So did you use 40 for calcium? 40 plus 12 plus 48. The 3 only goes to the oxygen. Okay. Got it?
I did.
That's all right.
I did a different.
Oh, you use cobalt.
Yeah.
Yeah. Sorry, C, and this is a capital O, so that means we're oxygen. If it were cobalt, it would look like this, C with a little O. Anytime we have a capital letter, that means we have a new element. Okay, so if we're at 100 grams, we take 321 divided by 100, right, because we've canceled grams, and that gives us 3.21 moles. Would we agree on that first one? 3.21. Check our answer. Is it reasonable? Right? If we know 1 mole weighs 100 grams and we started with 320, right? We started with 3 times more than 1 mole, so we should end up with 3 times more than 1 mole, right? 3.2. All right, very good. On the second one here, we calculated molar mass of sodium chloride not long ago, and we had it at 58.5. Okay, so if we're going from moles to grams, we should multiply across. And what did we get for our final answer here in grams? Patrick, what'd you have?
77.22.
Perfect. Okay, when we're looking at grams and moles, the number of grams should always be higher than the number of moles, right? With the exception of hydrogen, in which they'd be the same. Okay, but grams should always be larger than moles, right? We started with more than 1 mole, so our answer should be greater than 58.5, which it is. Okay. Here's a little joke for you. Any ideas? Ha ha. Ha ha. Womp womp. Okay, so now we're going to convert from moles to molecules, or moles to atoms. Okay? So Avogadro's number helps us link the moles of a substance to the number of atoms of a substance. So when I told you 1 mole is equal to 6.022 times 10 to the 23rd atoms, 6.022 times 10 to the 23rd, that is Avogadro's number. That is a number you must memorize. Avogadro's? Avogadro's? Yes, I've heard that before. Okay, Avogadro's number, 6.02 times 10 to the 23rd atoms per mole, or molecules per mole, or baseballs per mole, right? We talked about it doesn't matter what substance we're dealing with, it's always going to be that many number of something per 1 mole, right? 6.02 times 10 to the 23rd of anything is equal to 1 mole of that substance. When I talk about molecules and atoms, do we know the difference between those two things? Okay, molecules is of a compound. So we have 1 water molecule, which would be H2O as a whole. Right? But if we're talking about atoms, that means I'm looking at just hydrogen atoms or just carbon atoms or whatever it is. Does that make sense? So a molecule means we're looking at water as a whole or carbon dioxide as a whole or salt as a whole, whatever it is. And atoms would be single atoms of an element. Okay. Those terms get used interchangeably a lot, even though they do have 2 separate meanings. But it's okay if we're using them kind of interchangeably. I use molecule a lot more often than I use atom, and sometimes I use them in the wrong place. So you'll see me do that. Okay, so now we're going to convert between moles and molecules, or moles and atoms. Guacamole, get it? Ha ha ha. You can say that one at dinner tonight. Okay? What'd you say? Yep. Yep. So if I have 6.02 times 10 to the 23rd carbon atoms, that means I have 1 mole of carbon atoms, which means I also have 12 grams of carbon atoms, right? Those all mean the same thing. They're just different units. Just like 100 centimeters is the same as 1 meter, which is the same as 0.001 kilometers, right? They're all different numbers, but they mean the same distance, right? We're talking about the same thing here. So lots of different units to identify the same amount of substance. Okay, if I have 0.73 moles of lithium, how many atoms are in that sample? So how many individual lithium atoms are found in this sample that has 0.73 moles? It's still a T-chart. We're still going to do the exact same thing. And we're going to start with what we know. Okay, so this one I start in moles, and I want to go to the number of atoms. Okay, so if I want to get rid of moles, it goes on the bottom, right? Moles of lithium. And I want to go 2 atoms. It goes on the top. So in these conversions, the mole, again, gets the 1. Okay, it still gets the 1. Because we can tell how many atoms are in 1 mole of anything. How many atoms are in 1 mole of anything, no matter what substance we're talking about? Yeah. Right? In any substance, it doesn't matter what we're dealing with, there's this many atoms in 1 mole. So it's way easier for us to give the mole a 1 than to try to say 1 atom is 6.022 times 10 to the negative 23rd, or some fraction of a mole, right? It's much easier for us to deal with 1 mole is this many atoms than to go backwards, right? It wouldn't even be that same number. It would be a different one. But okay, so when we're going moles to molecules or moles to atoms, we don't have to deal with the molar mass at all. All we're dealing with is Avogadro's number. That's it. Okay, so it's much simpler to go between moles and molecules because there's no exchange of the molar mass there at all. Okay, so we multiply across the whole top, divide by the whole bottom. Again, I'm going to strongly recommend that you use the EE button in your calculator. Okay, so I would take 0.73 times 6.022 second EE 23. 4.39 times 10 to the 23rd. And what's our units here? Good. Atoms of lithium, right? Because we're left with atoms. That's what we wanted.
So you don't have to write like the 606.
No, just 2 decimals is usually fine. Okay, I'm not too picky about that. Okay, so now this one's a little bit more difficult to check. Is our answer reasonable or not? Okay, we started with more than 1 mole or less than 1 mole. We started with less than 1 mole. So our answer should theoretically be less than 6.022 times 10 to the 23rd. Okay, is this less than 6.022 times 10 to the 23rd? Yes. Right, we're still times 10 to the 23rd here, and this is less than 6.022. Okay, so our answer is reasonable. That's not something that you have to do on all your problems. It's just a good way to make sure you didn't flip-flop your T-chart on accident or just do something silly. Okay, that's just kind of a way for you to double-check yourself. Okay, making sure we're in the ballpark at least. Okay, blah, blah, blah. Okay, try this one. If I counted out 8.23 times 10 to the 23rd grains of sand, how many moles of sand is that? Right, I have way too much time on my hand if I'm counting out individual grains of sand. But nevertheless, okay? If I counted this many grains of sand, how many moles of sand does that equal? Does it matter here that we're not dealing with hydrogen or carbon or lithium or anything like that? Does it make a difference? No, right? Because 1 mole is 6.022 times 10 to the 23rd of anything, okay, including grains of sand.
You said you just have to remember that?
Yeah, you need to have that number memorized. 6.022 times 10 to the 23rd. Not for tomorrow's quiz or anything, but for future. Next class, whatever. Wednesday. No, today is Monday. Our quiz is Wednesday. Okay, so we know that the mole always gets the 1. So how many grains of sand are in 1 mole of sand?
6.022 times.
Good. Do we need to find molar mass of sand? No, right? We don't care about the molar mass. We're just going molecules to moles or grains to moles or whatever it happens to be.
Oh, that's a 2.
Yes. When we divide by Avogadro's number, you need to be careful in your calculator. You either use the EE button or use parentheses. I'm going to be very explicit about that. If we're looking at moles, should we be getting a really big number, a really small number, a regular number? What do we think? Pretty small, right? Pretty small.